Hi again, Year 12, last video of the year, your last video of Year 12. I am going to start Year 13, assuming that you've all done the videos. Okay, so please, if you have fallen behind, catch up. I guess the fact you're watching this video indicates that you're not behind. But yeah, let's make sure we're all starting from the same point. So we've been talking about functions, and today I want to talk about composite functions. I mean, let's just imagine you've got a manufacturing process whereby your raw material goes through two separate procedures. So this might be one procedure and this might be another procedure. And each of those procedures affects the temperature of your raw material. So let's say the effect of the first process can be described with a function. So x would be the temperature in and f of x would be what comes out. And then this second process has a separate and different effect on the temperature of your raw materials. So that could be described as g of x or whatever letter I wanted. Can't use f of x because I've already used it here. So if I take some raw material and put it through both processes, it's affected by both functions. And so this is what we're talking about with a composite function. In effect, using the sort of the mapping diagram approach, we are taking a value and putting it through the first process, so the value that comes out is whatever f of x does to it. But that new value, that f of x value, becomes the x value that goes into the next function. And so what we have is g of f of x. And I'm going to write that again over here because it's a bit odd. Now we could write it like this. Because that's what happened, isn't it? We've put x value has gone into the first function, and that's been changed into a new value, which we're calling f of x. And then that value is the x that goes into the second function. We don't put the double brackets, we just write it like this. So this is how we describe a composite function. This is the effect of taking an x value and putting it through one function, followed by another. The order is important. And I always think it's the wrong way round. This notation here means f followed by g. And the way I get my head around it is I think, okay, let's think about the journey of the x. The x is going to meet f first, and then it's going to meet g. So it's that way there. So this notation here means that fg of x would be the reverse, g first followed by f. And that's the most important thing to get your head round with these composite functions. The order of the letters is important. Okay, so let's look at an example. So here we've got two separate functions, simple functions, x squared and x plus 1. So we're going to put some numbers into those two functions. Okay, so we're firstly asked to work out fg of 1. That is, not going to draw a picture for all of these, but that's if you put a 1 into g first. So out will pop a 2. And then that is the x that goes into this function. And 2 squared, out pops 4. Remember, this is just a statement of the domain. X can be any real number. There's no limitation on x in that situation. Okay, think about this one. Think about this one. And then think about what would happen if instead of a number we just put an x through. Pause and have a go. Okay, I said I wasn't going to draw pictures for all of them. I am. So this one, I put a 3 into f first, so it goes into x squared. So out will pop a 9. And that then goes into g. X plus 1, sorry. Okay. So out will pop 10. And here I'm putting a minus 2 into f. So that's x squared. So out will pop a 4. And then it goes into x squared again. That will put equals 16. So the first thing we need to be able to do is to put values into composite functions like that. Here, what's the overall effect of taking a number and putting it into G and then in F? We can describe that as an overall combined function. So let's draw a picture for this. So I'm going into G first. So what G does is it adds 1. So what pops out is x plus 1. And this is the key thing. I then go into F, and that thing there is the x that goes into F. So F is taking what number you put in and squaring it. So it's going to be that squared. So gf of x, sorry, the order is important, fg of x is x plus 1 squared, which you could have multiplied out, and that would have been brilliant. Let's just check. I'm saying the order is important. What about gf of x? What about if I put x into f first, and that's squaring it, so out pops x squared. And then this thing here is the x that goes into g of x. So g of x is just taking whatever you put in and adding 1, so out pops x squared plus 1. Easy peasy, provided you remember the order. It's going this way. Let's have a look at another example. Okay, 2 more functions. Again, fairly straightforward. X can be any value in either of them. So have a go at defining fg of x. So we're not putting a number in, we're putting an x in. Remember, x is going to go into g first and then f. And then gf of x, and then f squared of x, which is the same as ff of x. That's x going into f, and then into f again. Hopefully you'll be able to do that fairly simply. And then we've got an equation to solve. We're going to go through that one in just a moment. Pause and have a go. Okay, so fg of x, x goes into g, and so out pops, so that's g, out pops x squared plus 4. That then goes into f, so f takes 3 of whatever you put in, which is x squared plus 4, add 2. So it's 3 lots of x squared plus 4, add 2, and I then multiplied it out. So that was 3x squared plus 12, plus another 2 gave me that. Gf of x, so x goes into f first, so out pops 3x plus 2, and then it's x squared plus 4. This is now this, so we do 3x plus 2 squared plus 4. I gridded that out, I added 4, and I think that's what you get, 9x squared plus 12x plus 4 plus 4, yeah. And then f squared of x, ff of x, x goes into f, out pops 3x plus 2, and it then goes into f again, which is 3 lots of whatever you put in plus 2. So 3 lots of 3x plus 2, that gives you 9x plus 6, plus another 2. There you go. So for this last part here, I've already defined fg of x. It's that. If I hadn't, then that would be the first step in solving this equation. But I've already defined it, so all I'm asking is when does that equal 62? And take away 10, take away 4. Oh, sorry, thought you could see what I was doing. There we go. So we've got 3x squared plus 14 is 62, so take away 14, divide by 3, square root. Okay, one more example to have a go at. Okay, one final example, the last example I'm going to work through with you in year 12. There's a tear in my eye as I write it. So we've got 2 functions, and note I've used that alternative notation which cropped up the other day. It just means the same. I don't know why we use it, it's so annoying, but there we go. This just means exactly the same as f of x equals, or even y equals. The reason we don't use y equals is because we need to differentiate between the 2 functions, so we call one f and one g and one h and one whatever. Yeah, what we're just basically saying is the effect of f is that x becomes this. That's what it means. The effect of g is that x becomes that. It's just a way of, I don't know, making it more complicated. Notice we've got a modulus function here as well. So go on, do fg of 3 for me, and then we'll have a go at solving this one. Pause and have a go. Okay, so fg of 3, that means I'm going to take 3 and put it into g first. So that's going to do 3 plus 1 divided by 2, so 2 comes out. And then I'm going to put that into f, so that's 2 lots of 2, 4, take away 8, which is minus 4, but it's the modulus of that. So hopefully you got 4 for that. So we put 3 into G first, 2 pops out, we then put 2 into F, minus 4 pops out, but it's modulus, so it's plus 4. Okay, so this function involves fg of x, which we haven't yet defined, so we need to do that. So let's, instead of putting a number, we're going to put x in. Okay, so we've got x plus 1 over 2. And we're then going to put that into f. So it's going to be 2 lots of this. Well, that's nice and easy, because if you took x plus 1 over 2 and then you double it, you just get x plus 1. So what comes out is the modulus of, that's x plus 1, minus 8. So fg of x is the modulus of x minus 7. And we're asked to solve, when does that equal x? Are you happy that x plus 1 take away 8 is x take away 7? This is a modulus equation. We were solving modulus equations just a couple of days ago, and you may remember that I always encourage you to do it with a graph. So I'm going to plot y equals that and y equals x. Remember, this is going to be a bounced curve, and we'll have to see where the two curves intersect. Go on. Final pause, and come back to me when you've had a go at solving that one. Now this emphasises, I think, the importance of doing a sketch, because if you just said, well, I know from last week it's either going to be when x minus 7 equals x, or when minus x plus 7 equals x, and you solved those two equations, you wouldn't have got the right answer, because the issue here is that both lines have got the same gradient. So y equals x minus 7 would be like this, all the way going through minus 7. But it bounces and bounces up, so it goes through plus 7 instead of minus 7. So I'll just go down to minus 7. There we go. And y equals x is just goes through 0 with a gradient of 1. And I deliberately drew this one accurately. I know you can't do that in an exam, but I deliberately did, just because it shows that these two lines are parallel, never going to meet. So this is my only intersection. So the intersection is where y equals x crosses the bounced section of the green line, which, if you remember, is the minus version. So that's minus x plus 7. So my solution, this point here, the only point, I'll call it A, but there's only one of them, is where minus x plus 7 equals x. Add x to both sides. X equals 3.5. And remember, these equations have no mention of y, so although we're using a graph, we don't need to work out y values. We just need the x values in our answer. Okay, so in the textbook, page 34 and 35 is where you'll find practice of this. If you're a bit unsure, question 1 and 2 just give you some basic practice. But for those who have found this okay, I strongly recommend you have a go at 3, 5 and 8 on those 2 pages, and question 3 is specifically the one I would like you to submit, your last submission question. So when we are back in September, hopefully in my room, hopefully with my lovely smart board and everything all back to normal, I will assume that you've all got to this point, and we will start perhaps with a little half-an-hour reminder, but we will then move on to the next thing, which is inverse functions. Having done a function, how you undo it. Okay, I hope you have a great summer and that you take care and stay safe. See you all soon. Bye-bye.